Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at approximating solutions to systems of first-order initial value problems. So in this topic we will give a description of systems of first-order initial value problems. We'll discuss their solutions if they can be found. We'll describe how operations that we used to approximate a solution to a first-order initial value problem can be translated into vector space operations of vector addition and scalar multiplication to approximate solutions to systems of first-order initial value problems. We will then look at converting our first-order solvers to being able to approximate solutions to systems of first-order initial value problems. And we will go over some examples. Now, suppose that we have a system of two first-order initial value problems. So you're going to notice that these two initial value problems are actually coupled in their differential equations. The derivative of the first depends on both the value of y of t, but it also depends on the value of z of t, and the value of the derivative of the second function also depends on both the first and second functions. We have initial conditions, specifically y at 0 is equal to 1 while z of 0 is equal to 2. Now, from calculus, you can find that this does indeed have a unique solution. And it's actually not that hard to find because the above equations are actually of a very special form. They're actually, if you'll notice, it's a linear equation. However, these are the two solutions. And if you were to substitute t is equal to 0 into the first, you would get a value of 1. Whereas if you were to substitute t equals 0 into the second, you get a value of 2. Consequently, the initial conditions are met. However, simultaneously, if you were to differentiate the first, you would find that the derivative is the negation of the first minus twice the second solution, and the derivative of the second is equal to the negation of the second plus twice the first solution. All right, so under certain conditions, we can actually easily find the solution to a system of initial value problems, specifically when they are all linear equations. Unfortunately, all I have to do is multiply the first term of the first equation by t. So now I have a second system of two first-order initial value problems. However, there is no known analytic solution to this particular system of initial value problems. It has a solution, but we cannot write it down in a closed form as we did for the above problem. So the only way we can determine or estimate what the solution is to approximate this solution numerically. Here's another system of two initial value problems. And again, you will see that they are coupled. We described this previously. This is the Lotka-Volterra equations. And here we have the initial time t0 is equal to 0 and two initial conditions. Here is a system of three initial value problems. And as you can see, they are coupled. So the derivative of x of t depends both on x and y. The derivative of y of t depends on x, y, and z, as does the derivative of z. And again, we have an initial condition that at time t0 equaling 0, all three of these functions are equal to 1. Now this second initial value problem is a collection of three equations called the Lorenz equations. And this introduced the concept of chaos theory into mathematics. What's really fascinating here is the reason this was so revolutionary at the time is a result of initial value problems approximations. The equations that we saw on the previous page are a result of analyzing and modeling natural systems, specifically weather patterns. The individual, Lorenz, was approximating this numerically. And so it was rather fascinating what happened. He was approximating the values numerically, and he was looking at the solution to this. Now, in this image, you can see a dot traveling around. What that dot represents is, in 3 dimensions, the position of the solution in the 3 directions x, y, and z. And so you can see that over time, all 3 change, and it seems to create this almost butterfly image. Well, what Lorenz was doing was approximating these solutions numerically, and at one point he cut off the equations and stuck in the numerical values back into the system as new initial conditions and move forward. What happened was very fascinating. Whereas for a short little while, the solution was following the same trajectory, very quickly it started diverging almost catastrophically away from the original solution. What was happening here was the data he was printing out was only to 6 or some odd significant digits, whereas the computer was probably storing them to floating point precision, which would have been 8 significant digits. Consequently, there was a small error in the initial conditions, and yet that small error resulted in a massive change in the solution after only a short little while. All right, this is an aside, but this particular image and those equations are the origins of what we now call the butterfly effect. After all, do these 2 circles not look like butterflies? And on top of that, this was discovered specifically because Lorenz was attempting to approximate these solutions numerically. Now, how could we approximate a solution to a system of first-order initial value problems? What approach could we use? Well, we have 3 equations. Let's create a vector-valued function. So let us assume that u is a vector-valued function where the result is a 3-dimensional vector. The first entry is the first solution x of t, the second entry is the second solution, and the third entry is the third solution. So normally, of course, we would write this as u1, u2, and u3 if we were referring to a vector-based approach. So rather than x, y, and z, the vector-valued function is u, and therefore the 3 entries are u1, u2, and u3, all 3 of which are functions of t. Now, the derivative of this vector-valued function is simply that vector-valued function that differentiates each of the 3 entries. So again, using vector notation, we'd have the derivative of u1, the derivative of u2, and the derivative of u3. Okay, so this is more or less the same approach that we would have taken before. In secondary school, you saw a system of 3 linear equations. In university, you converted that into a 3 by 3 matrix, and the solution you were looking for was a 3-dimensional vector. Now, it's always possible to define a vector-valued function. So here, for example, is a vector-valued function where each of the 3 components is some function of t, and we can calculate the derivative. And the derivative is simply the derivative of the 3 entries. The derivative of the first is 1 plus cos t, the derivative of the second is negative sine of t, and the derivative of the third is derivative of the first, copy the second, plus copy the first, derivative of the second. Now, a 3-dimensional vector-valued function of a real variable could represent many things. In the Lorenz equations, it represents the state of a weather system. However, it could also represent the x, y, and z coordinates of a drone at time t. And of course, at time t, the drone is in exactly one position. It could be the voltages at 3 nodes within a circuit at time t, and over time, those voltages may change. Or you may have a system that is reading 3 separate sensors, and so the vector may be the temperatures at 3 different sensors at one specific time t. And of course, over time, the temperatures of each of those sensors is going to change as it is reporting on what is occurring in the real world. You could, of course, have 50 sensors or 50 drones. The first would result in a 50-dimensional vector-valued function of a real variable, whereas 50 drones would not only have a 50-dimensional, but a 150-dimensional vector-valued function of a real variable. 150 because each drone has its own x, y, and z coordinates. Now, in each of these cases, the derivative of that vector-valued function gives you an instantaneous rate of change of whatever is being measured, be it a position, be it the rate of change of voltage at the 3 nodes, or be it the rate of change of the temperatures at each of the 3 sensors. So, specifically for the drone, this could tell us exactly how fast the drone is moving in the northerly direction, the westerly direction, and how fast it is moving in the vertical direction up. And of course, a negative in any of these would mean a movement in the direction south, east, or vertically down. Suppose, for example, you had a drone that was flying in a figure 8 over some region. Well, it's not actually a figure 8, it's actually an 8 with 3 loops, but nevertheless, suppose that the drone was following this pattern. In this case, you could give the speed in each of the 3 directions by calculating the derivatives, and this would also give you the direction of travel at any one moment in time. And notice that in the 3rd direction, the derivative is 0. That means there is no change in the altitude. It is simply a drone that is moving at the same altitude in this particular pattern. The speed of the drone at any one time is therefore given by this expression here. And if you were to plot this, you would see that this indicates that the speed of the drone is varying anywhere between 5 meters per second and 31 meters per second, assuming, of course, that the vector-valued function is in meters and the t-value, or the parameter, is in seconds, in which case the derivative is in terms of meters per second. Now notice that we have a position vector u and a velocity vector v. So, for example, here we have an object, the location of which is specified by a vector u relative to some origin. And this object is moving according to some vector v that tells the displacement per unit time, say meters per second. Then, assuming that the velocity is constant, we can actually, of course, estimate the position of this object one time step into the future by simply adding to u h times v. So, for example, if h was equal to 2, we would have h plus 2v, and that would be the new position after 2 seconds. Well, can't we do sort of the same thing with differential equations or initial value problems? Here we have a system of two initial value problems. We will define u to be a vector valued function that is two-dimensional. Its derivative is the derivative of each of the entries. We know, therefore, that the derivative of this vector valued function is simply this vector that is two-dimensional, where each entry is an expression in terms of the entries of the vector u. So essentially, this is a vector valued function of two variables. The first variable is the time variable or independent variable t. The second is the position vector u. So the rate of change depends on the time and the current position. On top of that, at time t equals t naught, in this case equaling 0, we have the initial position, and that initial position is a two-dimensional vector. Here's another differential equation we were looking at. Once again, we can write down the derivative of a two-dimensional vector valued function as we see here, and again, this right-hand side is a vector valued function that depends both on t and on the vector u, which are the two entries u1 and u2. And in this case, the initial value is this vector valued function at time t equals 0 is the vector 1, 2. We can do the same for the Lorenz equations, where we have three initial value problems. Now, u is a three-dimensional vector valued function where each of the entries depends on t. The derivative is simply the derivative of each of these entries, and the derivative is equal to a vector equaling the right-hand sides of each of these equations. And as you can see, we now represent x, y, and z as u1, u2, and u3. So this is our vector valued function of the independent variable t and the position vector u. Of course, we also have our initial condition at time t equals 0. The three values are 1, 1, and 1, although you could choose whatever you needed at the time. Well, let's see how this works with Euler's method. So essentially here we have our initial value problem, or system of initial value problems. The derivative is a vector valued function of the independent variable t and the position vector u, and we have the position at some initial time t naught, and that is given in some vector u naught. Now, as we discussed before, assuming that the velocity vector is approximately constant, then the position one time step into the future is the current position u0 plus h times the velocity vector, or the derivative, evaluated at time t naught at the initial position u0. Well, that just looks like Euler's method. So, given an approximation at time tk, where the approximation is the vector uk, our next approximation, uk plus 1, is just uk plus h times this vector-valued function evaluated at tk uk. Let's see if this works with Heun's method. Now, you'll recall with Heun's method, we calculated the velocity vector at time tk at the position uk. However, then we calculated a second slope, or second, in this case, velocity vector. Notice that our two arguments are tk plus h. H is a scalar. Time, being a scalar, plus a scalar gives us the next time step into the future. However, notice the next one is a vector uk plus a scalar times a vector of the same dimension. So that actually does work out. So now we've calculated or approximated two slopes. And so therefore, the approximation one time step into the future is uk plus h, a scalar, times the average of two vectors. The two vectors are two different velocities. And therefore, when we add them together and multiply that by the scalar h over 2, we get the average velocity across the interval from tk to tk plus 1, at least approximately. And thus, uk plus 1 is assigned uk plus h over 2 times the sum of two vectors. All of these are valid vector operations. Let's see how this works with fourth order Runge-Kutta. We found the first slope at time tk at position uk. We then added to tk a half h, and we added onto uk h over 2, a scalar, times the first velocity vector s0. We did something similar to calculate the third slope s2 and the fourth slope vector s3. Notice that when we approximate uk plus 1, it's the previous vector plus the scalar h over 6 times a linear combination of the four vectors s0 through s3. These are all valid vector space operations, and these do indeed work as expected. So consequently, all three of our algorithms, and as you may suspect, so do the Euler-Heun adaptive methods and the Dormant-Prince method. So that's nice, because we really don't have to do much. Now let's recall our implementation of Euler's method. We're returning a tuple of 3 pointers to arrays. The first argument is a function that takes a time variable and a position variable, and it returns the rate of change. The second one is a pair that takes the t range, the t0, and the final t value. Then we have the initial condition y0 and the number of steps. We calculate the h, which is the difference between the final t-value and the initial t-value, divided by n, the number of steps, and then we allocate our 3 arrays of capacity n plus 1, because after all, n gives us the number of intervals, which is 1 less than the number of points. We calculate the first, or we assign the first t-value, the first y-value, and the first slope by calculating the function at the initial t-value and y-value. We then carry on iterating by calculating the next t-value, the next y-value, and the slope at that next position, and we return that tuple of those 3 vectors. Let's update this function so it can solve a system of first-order equations. So now we are returning an array of t-values, but an array of vector values and vector slopes. The first parameter is a function pointer that takes a double as a first argument, the t-value, and a position vector as the second, and it returns a vector presumably of the same dimension. The time interval is left unchanged. It's a pair of doubles, but the initial value is now a vector. And of course, we have the number of intervals into which we are breaking this larger interval into. So consequently, h is unchanged. We calculate it by calculating the difference divided by n. We allocate 3 arrays. However, now the second and third arrays are arrays of vectors and not doubles. But that's the only change. We initialize the first time with the left-hand endpoint of the range. We initialize the first y-value with the initial y-value, which is indeed a vector. And we calculate the slope at this initial value by evaluating the first argument, the function f, at the double t0 and the vector y0. If you'll notice, there's no change to the for loop. The next t-value is the previous t-value plus h. The next y-value is the previous y-value plus h times the slope at that y-value. And then we calculate the slope at the next value by evaluating the function f at the current time and position. And then we return that tuple. So more or less, other than the type names, nothing has changed. Indeed, really, nothing has changed. All of this worked because when we implemented the vector class, we overloaded all of the operators. Consequently, any operation on doubles equally works for 2 vectors. This includes, for example, the unary negation operator and the unary neutral operator, or plus. We also implemented all of the auto assignment operators, such as plus equals, times equals, etc. Consequently, there was no change required to the algorithm. We can even make similar changes to the dormant prince algorithm. Actually, there was only one additional trivial change that was required for the adaptive algorithms. Specifically, we were comparing 2 approximations using the absolute value function. However, the absolute value function is not defined for vectors, and so we had to replace that with a call to the norm. For example, at the start of the class, I introduced this system of two first-order initial value problems, and I provided the solution. So at the bottom, here we see the two solutions plotted as bold functions and the approximations found using the adaptive Dormant-Prince algorithm. And as you can see, initially, obviously the step size h was far too small, and it kept on doubling until the width of h was sufficiently large to get a reasonable approximation. Now, the greatest issue I find with students is the writing down of, or the conversion of, the system of initial value problems, or ODEs, to a function. So in this case, again, the function takes a double t as a first argument, but a vector u as a second argument. What is returned is a two-dimensional vector where the first entry is t times the first entry of u minus twice the second entry of u, and the second return value is the negation of the second entry of u plus twice the first entry. The initial condition is just the vector that is two-dimensional containing the entries 1 and 2. Now you'll recall from the start of this talk, this second initial value problem does not have a solution that is in closed form, that is, an expression that we can demonstrate is actually that solution. However, we can still pass this function to Dormant-Prince, and Dormant-Prince will provide an approximation. Now, before we carry on, consider stopping the video now and write down the function for the Lorenz equations. All right, assuming you've tried this question, so now the right-hand side of the differential equation is this vector that takes a double t as a first value and a position vector as a second value. It's going to return a three-dimensional vector. The first, and what we will do is anywhere where we see x of t, we will replace that with u at 0. Y of t is replaced with u at 1, and z of t is replaced with u at 2. Having made all those changes, that's exactly what you see there. So, again, reasonably straightforward. And of course, the initial condition is a three-dimensional vector where all the values have the value 1.0. Let's now go the opposite direction. Suppose that you were given this function representing the right-hand side of a system of initial value problems. Well, the first thing we note is that the dimension of the vector is 3, and therefore we have a system of 3 initial value problems. They're all first order, of course. So let's call these 3 unknown functions x, y, and z, each of them functions of t. So the first expression, or the first entry, says that the derivative of x is equal to negative x of t, because u0 is representing the function x, minus the product of y of t times z of t. After all, we have u1 and u2, so u1 represents y, u2 represents z, plus t squared. The second is the derivative of y of t is negative y of t times z of t, for we have u1 and u2, plus 2.5 times t. And finally, the third is the derivative of z with respect to t is negative z of t minus x of t plus sine of t. Now, following this topic, you hopefully have a deeper appreciation for systems of initial value problems. You understand a system of initial value problems can be converted to vector form. Consequently, we can solve such systems approximately using vector expressions. You now know also that this requires essentially no changes to solvers. After all of the arithmetic operations seamlessly translate to either vector addition or scalar multiplication, and as long as our vector class implements all of these operators, everything should work. In fact, this is one of the primary reasons we introduced a linear algebra vector class instead of using the standard template library vector class. And you also know how to formulate such problems so that you can call the appropriate solving function. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!